Okay, then I will just start with my presentation. Thank you very much for having me here. As you know, we all followed the COP26 in Glasgow last month, when the world government negotiated the conditions for abandoning fossil fuels. This affects the way we produce electricity maybe more than anything else. Fossil fuels have to be replaced by other means of energy production. Even if the energy is harvested from regenerative alternatives, it still requires resources. And these resources are limited. Therefore, I want to talk today about a way to control resource consumption called EcoPoint concept. This is the content of my presentation. As we face climate change, it is not sufficient just to avoid gas, coal, and oil, but energy has to be provided by alternative processes. This is not limited to the production of electricity or the provision of mobility. Many industrial processes require fossil fuels as an elemental input. You have just to think about steel and cement production or the organic chemistry. If production shall continue, fossil fuels have to be replaced by other types of resources. The logic in the past was that when one resource is not available anymore, industry and economy would look out for replacement and make use of it in the same fashion as before, without considering the consequences. We just see where the consequences can lead to, and the shift to alternative renewable energy sources require other types of resources with other types of consequences. Just as an example, plastic production on fossil fuel as a feedstock, if this fossil fuel should be completely replaced by renewable biomass, this would require more than 1 million square kilometer of additional agricultural land, comparable to the total areas of Germany, Switzerland, Austria, and Italy together. And this in competition to food production and energy demand. Even if wind or sun is used for energy generation, more mineral resources are required instead. This shows that we need a new concept of resource management. And this concept that values resources and keeps them in the cycle. This transition requires investment and leads to a rising price, we can see this in the moment in the energy market, where uncertainties drive the prices for gas and oil. Recently, many people in developed countries suffer from higher energy prices for heating, electricity, and transport. People in developing countries suffer even more because they have to deal with mitigation and adaptation measures they cannot afford. The developed countries promise, therefore, to support developing countries with annually $100 billion, but did not deliver yet. And people will only support the transition if they are able to bear the cost. Many people in not only developing countries, but also in developed countries may not be able to do that. Therefore, I introduced a concept that uses resources consumption as a measure for the ability to provide monetary compensation. The thought behind this is that consumers with a high consumption are able to provide compensation to those who cannot afford this. In this concept, the exploitation of resources is taxed with eco-points as a kind of resource currency. And these eco-points are emitted by an eco-point central bank and distributed equally to the worldwide population. Every person is provided with the same amount of eco-points. The consumers use their eco-points to purchase the resources incorporated in products they buy. Unused eco-points can be traded between consumers. Consumers who require more buy them from those who cannot afford to use them. By this, eco-points move upstream from markets to producers to the exploiters of resources. These have to return the eco-points to the central bank for the right of exploitation. Resource recovery, as you can see here with recyclers, do not require the use of eco-points for their business. Resources that are taxed in this concept are fossil fuels, biomass in the form of land use or wood, and minerals. Here you can see a selection of resources and their prices. It ranges from fossil fuels between 3 and 4 eco-points per kilogram. Abiotic resources are, for example, iron with a price of 0.12 eco-points per kilogram, or gold with a price of about 100,000 eco-points per kilogram. The use of arable land requires 0.35 eco-points per square meter and year, and the cost of 1 cubic meter of wood is around 1,000 eco-points. A more complete list you can find in my paper that the reference you find at the bottom of this slide. This concept has some important consequences. The number of eco-points is limited by the amount emitted by the central bank. Therefore, no more resources can be exploited than the number of eco-points available. That is, an effective resource cap is established. Of course, it is not reasonable to believe that the resources enter the market in this way as are sufficient to support the growing demand. But I believe that this system provides an incentive to develop more efficient recycling processes and that most material can be kept in the material cycle. Moreover, by introducing an inflation rate, resource prices increase every year, while the individual share of eco-points remains constant. This shall reduce resource consumption until a sustainable level is achieved. Here you can see the current resource consumption shown as the required amount of eco-points. This is here. If we now look into the future, we can see that the amount of resources that can be purchased is decreasing. You may ask how we can allow a reduction of resource consumption without damaging the economy. And the solution is quite simple. 80% of the eco-points are currently used for fossil fuel. These act as a buffer for the system. The reduction of the resource consumption is mainly carried by the reduction of fossil fuel consumption. natural resources and mineral consumption is allowed to rise to some extent. From there, it is also possible to estimate how much energy from biomass would be approximately available. This was calculated from the land use allowed by the use of eco-points after subtracting the land required for food production. This does not include incineration of waste. Currently, about 60 XIU are used as bioenergy. Considering the limiting factor of the system, about 200 exajoule would be available at the end of the century. This means only a fraction of the future energy demand can be satisfied by biomass. This shows the protective effect of this concept that does not allow the excessive use of natural resources. From now, I want to show how the eco-point concept should affect resource consumption and electricity pricing. For this purpose, I select 6 types of energy sources: 2 fossil fuels, hard coal and natural gas, then wood as biomass, and hydropower, photovoltaic, and wind as other alternative energy sources. In the case of wood, wood chips are used solely produced for the aim of energy production. The use of waste wood would reduce costs significantly because waste materials are not taxed. The aim of this investigation is to know how the eco-point requirements change with the type of electricity production. Does it bring any advantage to abandon one type of energy and replace it by another one? Then, what resource consume the most eco-points? It is not necessarily true that the fuel consumes the most eco-points. Wind and sun do not require any eco-points, but the transport and installation of equipment does. What will be the price driver for alternative energy sources? And at last, does the change in electricity production cause also a change in the origin of required resources? What regions will profit and what regions will lose? The location for electricity production was, for all cases, Germany. Eco-invent processes were adapted by Axio-based data for multi-regional use. In the beginning, the eco-point requirement was estimated for all processes using eco-invent 3.3. Then undefined processes were used and upstream processes were added until 95% of the eco-point consumption was established. Unfortunately, this could not be reached for all electricity production processes because of their complexity. The eco-invent data could not be used directly because in this work an economic allocation was used. The reason for this was that when a process resulted in several products, the producer would probably decide by the market and not by the physical circumstances how to distribute eco-point prices. Just as an example, if gold and copper are exploited together, a higher price of gold is easier to establish than for copper. Therefore, the eco-point price for gold will be higher than that for copper. Here you can see the differences between the eco-invent database and the current work regarding the eco-point cost for different ways of electricity production. The price for electricity from wind, water, and sun is much lower than that from fossil fuel derived electricity, as we would expect. The price for wood derived electricity is somewhat in between, which is caused by the rather high price of wood. Wood is a limited resource that needs to be protected in order to make sustainable use of it. Interesting are the differences between this work and the EcoInvent database. The reason for the strong difference for wood are allocation and up and downstream effects that are commonly included in the LCA but ignored in the EcoPoint calculation. For hydropower, road transportation was responsible for 84% of all EcoPoints, which was probably more than suggested by the EcoInvent data. Anyway, if we look at the different resources classes, fossil fuel had a dominant role for most of the processes. Please be aware that this is only a relative impact. For comparison, you can see the small figure at the top, which keeps in mind the results from the last page. For the use of coal and gas, naturally other resources were negligible, but also for wind and water, more than 50% of EcoPoints resulted from fossil fuel. Considering that about 40% of the EcoPoints for photovoltaic are not allocated yet, we can assume that the same is true for sun energy. However, also the fossil fuel share reaches more than 60% for renewables. The absolute value of EcoPoints is much smaller, since these processes require less resources in total. Only in the case of wood, biomass dominated the EcoPoint price, since wood is quite an expensive resource in this concept. On the other hand, the impact of minerals can be neglected for all processes but photovoltaic and wind energy. Let's have a closer look on the fossil fuel consumption during the electricity production from hydropower. I already told that for processes generating electricity from fossil fuel, other means of fossil fuel use can be neglected. And hydropower does not directly require fossil fuel as an electricity production, but indirect input can be found. The largest share is required for road transportation during construction and operation. Another share requires the use of diesel for building machines for the hydropower plant and road construction. Additionally, bitumen is required for road construction. The remaining crude oil fraction is mostly used for other transportation services and the production of construction materials. Coal and gas is used for metallurgical processes and electricity and heat production. Regarding biotic resources, only wood and hydropower require a substantial amount of biotic resources. Wood incineration requires biomass and hydropower land use. You can see that wood incineration requires only small amounts of EcoPoints for traffic areas compared with the provision of biomass. For hydropower, most areas used are the result of artificial water bodies. Some minor impacts are related to traffic, and also some wood is used for energy provision. I included also minerals into the eco-point concept because the sustainable use of minerals is very difficult. They are mostly non-renewable, and renewable forms of energy production will put pressure on many metals. Mineral use for coal, gas, and wood is negligible because of the high prices for fossil fuels and wood. For the other investigated options, hydropower, wind, and photovoltaic, metals can become quite essential. Here you can see that each of these options has its own requirements. Wind and hydropower require steel, making use of iron, nickel, and molybdenum. Hydropower for reinforcing steel, and wind power for highly alloyed steel. Zinc is used for galvanization of metal pieces in the case of wind energy. Barite is used for crude oil production and therefore appears in the hydropower diagram. The mineral consumption for photovoltaic is very different. They are used for electronic parts, and because of their high prices, steel is of minor importance. The metal with the highest share is silver, which is used together with copper and tantalum for the production of electronic components. Aluminium is used for the panel installation. Hartwig et al., you can find the reference in the end of this presentation, were concerned that copper and aluminium supply may not be able to satisfy the future demand. I would like to add silver as a metal of concern, since the high share suggests high consumption compared to the still available reserves. Oh, that was too far. Here you can see the origins of the soil resources used. Most of the gas and wood comes from the region of electricity production. Wood is mostly harvested in Germany, and gas comes from the North Sea area. In the case of hard coal, I have to say the data are already a little bit older. Today, there is no hard coal mining in Germany anymore. So this would also be imported. For hydropower, resources provided in Germany are lignite and land use for hydropower generation. Countries like Russia, Norway, and the UK provide fossil fuels. Quite the same distribution is found for wind. Photovoltaics uses also lignite from Germany. Coal power for silicon production and silver comes from China and other parts of Asia and the US. When we have a closer look to minerals, we can see that especially the use of photovoltaic requires minerals. We have already seen that the mineral consumption needed for the generation of electricity from coal, gas, or wood can be neglected. Hydropower requires ferronickel from Indonesia and iron from Brazil. Wind power additionally think of from Sweden, Portugal, and Latin America. But these amounts are rather small compared with the requirements for photovoltaic. Silver is required from China and other parts of Asia, the US, Latin America, South Africa, and Australia. And additionally, copper and bauxite come from Latin America. You can see on the map that none of these minerals used were mined in Europe, which indicates a rising dependence on supply chains. But this dependence can be reduced by recycling. Especially specialty metals are not recycled today. The high price in this concept and the limited availability could promote recycling, since waste materials do not require additional eco-points. At the end, I would like to have a look at the prices induced by eco-points. Remember that eco-points are a monetary unit that can be traded between individuals. For this calculation, an eco-point price of 6.2 eurocent was assumed. You can see that the cost for electricity generation from fossil fuel are already higher than for alternative energy sources without considering eco-points. With these, they lose even more competitiveness. Half of the price for electricity generation from coal could come from eco-point. Also, the use of wood becomes more expensive when energy wood is used. Incineration of waste wood would reduce the price accordingly. The winners of these systems are wind energy and hydropower. Both have the lowest resource consumption. The price for photovoltaic energy generation could be reduced by enhancing recycling and the shift to alternative types of energy. Use of fossil fuel can be avoided and metals can be recovered. This is not possible for the use of fossil fuels. Once burned, they cannot be recovered. Therefore, my conclusions are: this concept promotes the sustainable use of resources, processes that do not allow the recovery of material become expensive, processes making use of resources for a long time become advantageous. Only burning a resource like coal, gas, or wood becomes less attractive. The recovery of resources is promoted, which is especially necessary for metals because these come more often from overseas regions. We can also see an increasing pressure on metals, especially on silver, which also increases the requirement for recycling. These are the references I would like to show. And thank you very much for your attention. If you have any questions, please let